Okay, so let's take a look at the example question on page 360 in the textbook. They ask us to find the binding energy of the nucleus of carbon-12. Now, carbon-12 again was very important because this was the foundation for the atomic mass unit. Remember, the atomic mass unit is the mass of a carbon atom, not a carbon nucleus, a carbon atom divided by 12. So to find the binding energy of the carbon nucleus, the first thing that we need to do is to find the mass of the nucleus. So to remind you, the mass of the nucleus is equal to the mass of the atom. In this case, the mass of the atom is exactly 12.000 U minus the Z number. Remember, Z number for carbon would be 6. And then I would multiply that by the mass of the electron, which is 0.05486 U. And this gives me a number of approximately 11.99671 U's. So this is the mass of the nucleus. Now the mass defect is going to be the mass of the individual protons and neutrons added together, and then I'll subtract out the mass of the nucleus, and I'll see that there's some missing mass. So in this case, the mass defect is going to be 6 times the mass of a proton, 1.007276 U's, plus there are 6 neutrons, and they have a mass of 1.008665 U's, and then I'll subtract from that the 11.99671 U's. And again, the symbol for this is the lowercase letter delta. Okay, so with that in mind, we multiply these two, and add them, and then subtract this, we would find that we get a mass defect of approximately 0.09894 U. So a relatively small mass defect for the carbon nucleus. Now remember, this is not the same thing as the binding energy per nucleon. This is the total amount of binding energy necessary to release all of the individual portions of the carbon-12 nucleus into individual protons and neutrons. So how much energy does that correspond to? Well, again, we would use the conversion factor that is that 1 U is equal to 931.5 MeVs, and we would calculate that this corresponds to approximately 92.2 MeV. So just to make it clear, this is not the binding energy. This is the mass defect. It's the amount of mass that's missing. To know what the binding energy is, I need to convert that mass defect into its equivalent form of energy. And this is why Einstein's formula E equals mc squared is called the equivalence formula, because it tells you the equivalent amount of energy that that much mass would account for. And so this is our binding energy. But again, when we look at the binding energy of a particular nucleus, it doesn't really tell us how stable the nucleus are. What we really need to do to find out how stable a particular nucleus is to look at the binding energy per nucleon. That's a much better measure. So we've had several examples. We looked at helium, we looked at the gold nucleus, and now we've looked at the carbon-12 nucleus. So let's figure out which of these guys has the biggest binding energy per nucleon. So let's start off for our example for helium. So for our example of helium, we found that helium had an approximate mass defect of 0.0304 atomic mass units. So this guy had a mass defect of 0.0304 U. Now that's a pretty small binding energy, but when we compare this to the binding energy per nucleon, we'll see whether this is actually a lot or a little. So let's first convert 0.0304 U, and for every 1 U there are 931.5 MeVs. So this turns out to be approximately 28.32 MeV. Okay, so now this is the total amount of binding energy, but what I'm looking for is the binding energy per nucleon. Remember that helium, sorry I should have said that in the beginning, helium has 4 nucleon, 4 nuclear particles. So what I need to do is, I need to find the binding energy per nucleon. I need to take the 28.32 and divide it by the 4 nucleon, and this is going to give me approximately a binding energy per nucleon of about 7.1 MeV per nucleon. And that's for helium. So let's go ahead and go in order of increasing mass. So for example, let's take as our next one carbon-12. Now we saw that carbon-12 had a mass defect of, in the previous problem, remember carbon-12 had a mass defect of 0.098984. So 0.09894, we make the conversion to energy, 0.09894, 1 U, that's in U's. 1 U is equal to 931.5 MeV. And so that gives us an approximate energy for, oh, we actually did this conversion already. We knew that that was 92.2 MeV. So if we take that 92.2 and divide that by the total number of nuclear particles, or the total number of nucleon, there are 12 nuclear particles, so I would divide that by 12. That gives me an approximate binding energy per nucleon of 7.68 MeV per nucleon. So it turns out that the carbon nucleus is actually even more stable than the helium nucleus. Now both of these are very stable nuclei, but relatively speaking the carbon nuclei is more stable than the helium nucleus. So let's look at one last example, and that is now we found the mass defect of the gold nucleus to be approximately 1.67 AU. So sigma is equal to 1.67 U. So our first step is to convert that into energy. And this turns out to be approximately 1,555.6 MeVs. So now I will take the 1,005. Now that's a huge amount of energy. Look how much more it is than the previous ones. Doesn't necessarily mean this is more stable, because look how many nucleons there are. 197 nucleons. So I need to divide this number by the number of nucleons, 197, and this turns out to be approximately 7.89 MeV per nucleon. A little bit more stable. Now you shouldn't think that the atomic nuclei get more stable as they become larger. There is actually a point at which the nuclei begin to actually decrease in value, and 7.89 actually is not the highest value for an atomic nuclei. When we look at the curve on page 361, we'll see which of the nuclei, not these three, but which of the nucleon is actually the most stable and has the highest binding energy per nucleon. It actually exceeds 8, whereas these guys are all just a little bit under that 8.